Utility companies maintain control through precise measurement of kilowatt hours consumed, defining the boundary between corporate resource and consumer access. Electricity theft, technically known as unauthorized abstraction of electricity, exploits vulnerabilities in this measurement infrastructure. All residential power consumption relies on the principle of integrating power over time. Power, measured in watts, is the product of voltage and current. Standard residential service uses alternating current, requiring meters to accurately track instantaneous power flow, accounting for phase differences between voltage and current, known as the power factor. The grid operates under the assumption of closed-loop accountability, where every electron flow is theoretically tracked back to a source and billed. Bypassing this system requires understanding how the meter isolates and quantifies the energy passing through it, specifically targeting the current sensing mechanism. The classic electromechanical meter, or induction meter, functions as a small motor driven by the load. It uses two sets of coils, the voltage coil connected in parallel across the supply, and the current coil connected in series with the load. The voltage coil creates a magnetic field proportional to the supply voltage. The current coil generates a field proportional to the load current. These two fields interact with a conductive aluminum disc, inducing eddy currents within the metal. The resulting torque on the disc is directly proportional to the instantaneous power consumption. This torque drives a gear train, registering the total energy consumed. The speed of the disc rotation directly indicates the rate of consumption, making it a visible indicator of power usage. Manipulating induction meters typically involves disrupting the magnetic fields or physically impeding the disc rotation. Strong external magnets placed strategically can saturate the magnetic flux paths, reducing the effective torque applied to the aluminum disc, causing it to slow down or stop entirely. The magnet must be positioned to interfere with the interaction between the voltage and current coil fields without completely stopping the meter, which would immediately flag suspicion. Another method involves drilling a small hole into the meter casing and inserting a thin wire or pin to physically obstruct the disc's movement. Alternatively, reversing the input and output wires can sometimes cause the meter to run backward, although modern induction meters often incorporate anti-reverse mechanisms or ratchets to prevent negative registration. Digital meters, commonly known as smart meters, replaced mechanical systems by utilizing digital signal processing. Instead of relying on induction and mechanical torque, these meters continuously sample the instantaneous voltage and current waveforms thousands of times per second. An internal microprocessor then calculates the true root mean square power consumption by integrating these samples. This digital approach eliminates the vulnerabilities associated with mechanical friction and external magnetic interference, which were easily exploited in older models. Smart meters also incorporate non-volatile memory and often communicate consumption data wirelessly back to the utility, enabling remote monitoring and disconnection capabilities, fundamentally changing the security landscape. Bypassing digital meters requires targeting the current sensing components or the computational logic itself. Most digital meters use current transformers or shunts to measure current flow. A common technique involves creating an external bypass circuit or shunt around the meter's current sensing terminals. This diversion allows a portion of the load current to flow outside the meter's measurement path, resulting in underreported consumption. More sophisticated attacks involve accessing the meter's service port to upload modified firmware. This compromised firmware can be programmed to report zero consumption or a fixed low value, regardless of the actual load, effectively neutralizing the meter's function and requiring specialized technical knowledge.
Phantom load techniques exploit the meter's reliance on accurate phase angle measurement to calculate real power. If the voltage and current waveforms are significantly out of phase, the true power measured decreases, even if the current magnitude remains high. This is achieved by introducing highly inductive or capacitive loads into the circuit before the meter. These reactive loads shift the phase angle, increasing the apparent power but reducing the real power registered by the meter. While this does not reduce the total current drawn from the grid, it manipulates the power factor, causing the meter to register less real power consumption. This method is complex because utilities often penalize commercial users for poor power factors, but it demonstrates exploiting alternating current physics. Utilities employ sophisticated detection methods to identify unauthorized abstraction. Smart meters are equipped with Tamper flags that trigger alerts upon detecting specific anomalies, such as sudden voltage drops, unusual current imbalances between phases, or the opening of the terminal cover. Remote monitoring systems analyze consumption patterns, flagging accounts where reported usage deviates significantly from historical averages or neighborhood profiles, indicating potential diversion. Furthermore, specialized equipment can detect the presence of strong external magnetic fields near the meter location, even if the meter itself is shielded. Physical inspection teams also look for visual evidence, including altered seals, bypass wiring, or heat signatures indicating unauthorized connections. From an anarchic perspective, utility infrastructure represents a centralized monopolistic control mechanism over essential resources necessary for modern life. Electricity theft is viewed not merely as crime against property, but as direct action against corporate resource enclosure and profit extraction. The act of bypassing the meter reclaims a resource deemed necessary for survival and autonomy, challenging the legitimacy of the billing system itself. This resistance highlights the vulnerability of centralized grids and the potential for decentralized off-grid solutions to negate the need for utility accountability entirely. The technical means of bypassing are thus tools for immediate resource liberation and challenging state-sanctioned monopolies. Executing a power diversion requires precise knowledge of electrical wiring standards. Improper bypassing creates severe fire hazards due to inadequate conductor sizing and unsecured connections, leading to excessive resistive heating. When diverting current around the meter, the connection must handle the full load current safely, typically requiring heavy gauge conductors and robust insulation rated for the maximum amperage. Series connections are inherently dangerous, as they interrupt the main circuit, while parallel shunts must be perfectly balanced to avoid overloading the remaining measured path. The primary risk is catastrophic failure at the point of unauthorized connection, endangering both the structure and occupants through electrical fire. The future of grid accountability moves towards distributed generation, where consumers also become producers through solar or wind power. This complexity necessitates bidirectional metering, tracking both consumption and injection accurately. Utilities are countering bypass attempts by integrating advanced encryption and hardware security modules into new meters, making firmware manipulation significantly harder and more expensive. Furthermore, utilities are increasingly installing meters outside the consumer's physical control, often on utility poles or in locked cabinets, minimizing physical access points. The ongoing technical arms race focuses on securing the physical interface and validating data integrity through cryptographic methods to maintain centralized control over resource flow.